Okay, so let's get started.
Yeah.
Okay. Okay, so last week we talked about dense reconstruction. So previously in the course we show how to get sparse point matches to extract cameras and triangulate points to have sparse reconstruction. Then in the last week we showed that how we can use this initial camera poses to get much more point correspondences for having a dense reconstruction. And we started by defining rectified stereo pairs such that the corresponding epipolar lines are just lines that are parallel to the x-axis. So therefore, it is only needed to find the disparity from each pixel of the left image to its corresponding pixel in the right image. Then, for in general, two images, we showed that it is possible to rectify them to get the same setup such that we just need to find disparity from each pixel in one image to its corresponding pixel in the second image. Then we can use disparity estimation algorithm that we discussed last week, and we find much more point correspondences, triangulate them, and having this dense reconstruction from two views. So we talked about the fact that it is limited to two views, and that we can't find the depth of pixel from one image if it is occluded in the second image. And therefore, we would be happier if we could use more images for inferring the depth of occluded pixels in the reference image. And previously in the course, we talked about structure for motion problem, where we are given much more than two images, in general n images, and we extract cameras and sparse reconstruction. But today we will talk about multi-view stereo, which means that we know the cameras and we have images, and the task is to find a dense reconstruction. And today we'll talk about non-deep learning approaches first, Zeng et al. Method and Schonberger et al. Method, which is a method that Colmap MVS pipeline is based on. We'll talk about it later, and then we will review the plane sweep algorithm and show a deep learning approach that uses this approach of plane sweep. Okay, so let's start with mapping with known depths. So in one of your exercises, you showed that if I assume that I have a plane, frontal-parallel plane in front of camera 1, and I know camera 1 and camera 2, and then I can map pixels on this plane from camera 1 to camera 2 using an homography that has closed form solution according to the depth and the camera parameters. Therefore, I have a homography that maps pixels from camera 1 to camera 2 when I know their depths. So now let's start to talk about Zeng et al.'s method. So the setup is that I have a reference image, and I want to estimate the depth of each pixel given several source images that you can see on the right. So in this case, I don't have only two images, I have general set of other source images. And I would like to predict the depth of each pixel in the source image. So for example, this pixel, which its x coordinate are L, y coordinate are Y, and I want to find its depth, which is denoted by theta L, the depth of pixel L. Okay, we will see later why we use these notations, but that's the notations for today. Okay. So as we saw in the beginning on the previous slides, given that I know the depth, and for example, this is the correct depth, then I can map this pixel to the source images because I know all the cameras in this case. So if the depth is correct, I will get a correct corresponding point in the source images. But if the depth is not correct, then the corresponding points will be wrong. So I will not get correct corresponding points. Therefore, in order to find what is the correct depth, I can use the normalized cross correlation metric, for example, and to try different depths. Each time, according to the depth, find the corresponding pixels in the source images. And if the patch around these pixels are similar to the reference image, I know that it is correct depth. So in this case, they are not similar. So I'll say that the depth is incorrect. But if they're similar, and I get high normalized cross correlation, I will say that my depth is correct, and I'll choose it. So that's the general case. But what happened in this case? In this case, even if I use the correct depth, this reference pixel is occluded and cannot be observed in image 2, as you can see here. So if I apply this mapping, I will map it to a pixel that doesn't look like my reference pixel. Therefore, even with the correct depth, I will get low normalized cross correlation for this correspondence in source image 2, and high normalized cross correlation for this pixel, the corresponding pixel from image 1. And let's see another similar example. This pixel, this reference pixel, can be seen in image 2, but it's not in image 1. So again, if I use the ground truth depth, I'll still only get high normalized cross correlation for source image 2. So that's a major problem, because I need to also know which pixels are observed for each reference point in each source image. Therefore, what they suggest is, in general, to get an input of source images and reference image, and this task is to find the depth map of each pixel in the source image, and to have probability maps for each reference pixel to be observed in each source image. And this, here they show this probability maps. So let's see how it works. So for example, this reference pixel is not observed in source image 1, but it is observed in source image 2, then I'll get this probability map for source image 1. So it means the probability that pixel L is observed in source image 1. So in this case, it's close to 0. Then I know that I can't find this point in source image 1, so I will exclude it when I try to infer the depth of this point. But for source image 2, this pixel, pixel L, is observed, so I will not exclude it, and I will calculate the best depth according to the matching point in source image 2, and choose in this case theta 1, because I will get higher normalized cross correlation. Okay, until now the setup is clear.
Could you explain again, is it necessary that the reference image should be frontal parallel to our camera? Because
no, like, just for simplicity of the example, it can be any image.
Okay, could you explain why did you reminded us about the assignment from the sixth exercise from the first assignment? What does it have to do with this method?
Okay, first we'll use it several times in this lecture, but specifically here, the way I know how to map, if this pixel XLREF to the corresponding points is according to this formula. So I know this point. If I assume that the depth of this point is theta 1, then I need a way to map it to each corresponding point. So this mapping is done using this formula. I know the depth of this pixel, so I know how to map the patch, XLREF patch, to source image patch.
But that formula was true for planar scenes, right? And here we, what are our assumptions?
No, I can assume that this pixel is lying on some frontal parallel plane. So you are right that it might not be correct, and we will discuss it, but I can assume it and have this correct mapping. But I'll still get a correct mapping. We will see the disadvantage of this assumption, but in this case, yes, I assume that this reference pixel is on a frontoparallel plane and map it to this pixel according to a homography resulted from this assumption to different pixels according to the depth.
Yoni,
Yes.
a question. First, you said that we're using nearest correlation something, right?
Normalized cross correlation.
Normalized cross correlation between two images, right?
In
But
two patches.
because we have a perspective between two images, the correlation cannot be 100%. It can be even lower because now I have some different angle between the same area of the pixel to the reference.
Yes, it's not a perfect metric, but it's a metric, and there are better metrics. But for this, here I use the normalized cross correlation metric. For this example.
Also, you said you have for each pixel which image its probability it's seen, right?
Says ZL2 is a probability that pixel L is observed in image 2.
How did you obtain this?
So we will see. But suppose that I have all of this, then I know how to choose the depth. I know how to solve the problem that I described before for pixels that do not observe. I can just calculate the normalized cross correlation according to this.
And one last question, the previous slide, you had not more previous, you have depth images in the yes, deep depth map, but in the reality you don't have the depth map.
No, that's the output of their method.
Ah, this is the output, it's not the input of.
That's the input, output.
Okay, thank you.
Okay.
Can you explain the formula here, the notations, or what it means?
Which notation? I think that I described all of them. So can you refer to one that you think? What?
At the bottom.
Can you? I don't hear you.
Correlation is bigger than.
Yes, we showed the formula for normalized cross correlation in the last class. You can. It's just a metric to compare two patches. Okay, if it's high, it means that they are similar. If it's low, it means that they are not similar.
Yeah, okay. And the other terms here.
Which term?
Like X. It seems like L seems to be also a downscript and also upper script into different.
Okay, yeah. So let's repeat it. So L is the X coordinate of my reference pixel that I want to predict. We will see later why I needed to index the X coordinate, but that's what it defines. And theta L is the depth of this reference pixel, and X M L is the corresponding point in image M for this reference pixel L. Okay.
Theta one and theta one is the depth in the image one.
Yes, it's the correct depth, and theta two is a wrong depth, and I want to be able to choose the correct depth.
But the depth is in the world coordinate or in the image coordinate, or
no, it's in world coordinate. I have cameras, so I already have my units. Right, I don't have any ambiguity. I know the distance between the cameras. It can be in meters, centimeters, so the depth is according to these units.
Why it seems like the XL ref? Oh, okay. And the reference image is just one of the given images?
Yes.
Thanks.
Okay, so that's the input, reference image, and source images, and I want to predict the depth map of each point from the source image and the probability map for this point to be observed in each of the source images. And the motivation for knowing this probability map is that without probability map, I cannot count on normalized cross correlation if this pixel is not observed in the source image. Okay, so that was just a high level description, but now let's try to formulate it with some notations, mathematical notations. So they define a probability function for each corresponding patch given a reference pixel, depth, and the probability that it is observed in source image M. So it is defined as follows. If this pixel is observed in image M, then I can say something about the probability of this patch being a corresponding patch based on its normalized cross correlation with the reference patch. But if this if this reference patch is not observed, like here in source image 1, then I cannot say anything according to normalized cross correlation. I will just say that its probability is uniform. And there is some normalization scale for each of these terms, which is denoted by n, but it's not so important because they're canceled later in the computation, so you can ignore it. But generally, that just defines mathematically what we described in words in the slide before. Okay.
Can you explain again?
That's if the patch is in or not in an image.
Okay, sorry, what? Can you repeat the question?
Yeah, how we determine the Z?
Yeah, so we will see how we determine, but that's the definition of this probability map. We will use it to determine both the probability map and the depth. That's
Sure.
that's what we want to do. But first, we define this. What?
That is unknown.
Okay, so in this probability function, we assume that we're given Z, we're given theta when we're given the reference pixel. Okay, so that's the notion of given in probability notations. But I just want they define this probability metric for patch similarity in order to later all of this will be used to determine the unknown, the probability and the depth. Okay, but we just want to define what is described in word before in mathematical notation using a probability function. Okay, later, let's give some high level. Later, they will try to maximize the probability by inferring the correct depth and correct probability map. Okay?
Yoni?
Yes.
If Z here is the probability for the pixel to be in the source images, so what does P actually calculate or maps?
Rho, it's a normalized cross correlation. Okay, given that I know the depth, I know the corresponding points, right? For example, here, if the depth is theta 1, I will get this corresponding point. And if the depth is theta 2, I'll get this corresponding points, right? Based on the depth, I know how to map points from reference image to the source image. So now I have patches from reference image to the source image, and I can calculate the cross correlation between the patch to the mapped patch.
Okay, so P calculates the cross correlation.
Yes, a normalized cross correlation. It's between -1 to 1. And this actually, the first term actually measures the distance from my normalized cross correlation being 1. If it's 1, I'll get high probability for this being a correct corresponding point for this patch. And if it will be -1, I will get low probability. But I can use the cross correlation metric in order to determine the likelihood of this pixel being a corresponding point, given that I know given depth and visibility. So for example, in this case that it is observed, I can actually give the probability, give me some information about the likelihood of this pixel to be a corresponding point because it is observed. But here I cannot find any use with a normalized cross correlation because it's not observed. Okay.
Could you explain again? This probability is the probability of being visible on the image, or the probability?
Visible.
And why do we need these probabilities if we have like this these z's that tell us explicitly.
Yes, so I need to find both depth and the probability, but these two outputs are dependent on each other. So I need to find both, and that defines the relation between them.
I would say 1 for visibility, Z for visibility, and X for location. Maybe it will be clearer now.
Yeah. Okay, let's continue because I think that the questions will
just one last questions.
Okay.
Just here, for example, in the first source image, we see that when we change theta from theta 1 to theta 2, which means that we change the depth. So we end up with those 2 points. But I'm not sure how like you use the same index for the pixel, but you just change the depth, and we end up with those. Like I don't understand how we use the depth parameter here to pick different points in the image.
So I just define a probability function until now. We know how to map points from reference image to source image given the depth. Okay, we will see later how to choose the depth and how to choose the probability of visibility. But now I just define this probability function according to the cross correlation matrix. Okay, what?
There are more. It is possible that there are more than one.
Yes, this is just for this example, but I can use any number of depths and calculate this probability, right? For each depth that you give me, and each Z that you give me, and each reference pixel that you give me, I can calculate the likelihood of the matched pixel according to this formula. Let's continue. I think that will be more clear after you see the, the entire method. Okay, they also define a transition probability between the states of visible or not visible of 2 neighboring pixels. So they define the probability that a pixel is observed considering the situation of the pixel from the left, if it is observed or not. So basically, if gamma is high, it means that I want to keep the same probability between neighbors, and if it's low, it means that I let them change. So that's kind of smoothing the probability of visibility between neighboring pixels. Okay, so all what I described until now defines a graphical model, which I'll now describe. So this model is defined for 1 row of pixels from the reference image, which has L pixels. And then for each reference pixel, I need to predict its depth, which is defined here. Okay. And I need to predict the probability that it is visible in each source image. So for example, for source image 1, I get these probabilities, and also for other source images. And then, given that I know the depth, I can map each reference pixel to each source image, as you can see here. And then, as we described before, if according to its state, if it is observed or not, I can calculate the probability or the likelihood of this correspondence. So that's called a probabilistic graphical model. And then there is also this transition probability between states on this line, between pixel L to pixel L minus 1. And what you see here is defining a hidden Markov chain, which was very popular in the past. But here they find it useful for solving this problem of estimating both the probability that each pixel is observed in each source image. So for each pixel on this line, among capital L pixels, we want to estimate the depth of this pixel and the probability that it is observed in each source image. And this is done by maximizing the likelihood of the observations using this probabilistic graphical model. So I don't want to get into hidden Markov chain or HMM too much. I just say that they use this model, and this model defines likelihood for given the observations, that if I extract correctly the unknowns in this problem, where the unknowns in this problem are the visibility probability and the depth, then I can give likelihood for my observations, and I want to maximize this likelihood. So I'll estimate Z and theta, the depth and the visibility probability, by maximizing the likelihood of this entire model. That's the high level. And if someone interested in reading more about HMMs, I can give you reference to an excellent book. But that's the general strategy. So to maximize this likelihood, what is being used is the EM algorithm, expectation maximization, where there are two steps, the M step and the E step. So in the M step, some factors that define probability functions are searched for. So for in this case, we assume that we know all the visibility probabilities, and we're looking for the depth. So in this case, I know the probability that each reference pixel is observed in each source pixel, in each source image, and I use this to find the correct depth. In the E step, I will assume the opposite. I will assume that I know the depth, and I will calculate the probability that the corresponding pixel is visible in each source image. Okay. So they show that for estimating the best theta, given that I know the visibility, the solution is to minimize this function, which is actually a weighted sum of the cross correlations according to the visibility of the pixel. So I want to give more, for determining the depth, I want to give more weight to pixels that are visible for calculating the depth. But the problem here is that usually there are a lot of source images, capital M source images, and I don't want to go and calculate patch similarity for all the images. It will be too heavy. So what they do is they're taking this probability that pixel L is observed in the image M and normalize this probability over all the M images. So it's kind of give us probability for each source images for this decision making, for considering patch cross correlation to find the depth. So what they do is they sample a subset according to this probability function. So for example, this subset can be of size 15 instead of 300 source images, and then they maximize the cross correlation or minimizes 1 minus cross correlation over all this subset. So I think that it's intuitive, given that I know the pixel visibilities, I know how to use the cross correlation metric wisely in order to choose correct depth. But how do I choose theta star? What candidate I give theta star to be? So they use what's called patch match propagation, which was very popular a few years ago, where for considering theta star, they just use 3 options. First option is to use the depth of the pixel to my left. Second option is to choose my depth from the previous iteration. And third option is just to use a random depth. So it does 2 things. One is that it encouraged me to choose pixel of my neighbor and apply some smoothness in the depth estimation. And second thing is that it's very fast for each, for choosing theta L star here in this minimization, I just need to run 3 candidate depths and choose the best one. So it's very fast. And in the E step, we assume that we know the depths. So it's the opposite problem. I know the depths for each source pixel, for each reference pixel. And I want to find the probability that this pixel is observed in each source images. So this actually needs some HMM tools, and I'll briefly review what's called the forward-backward algorithm. So the idea is that I can base, if I know the depths, I can find these probabilities of pixel L observed in image M by having these 2 functions, alpha and beta. Okay, so we will see what they are. So alpha is calculated in a step called forward step, where each time I need to estimate kind of its probability, that the visibility probability of pixel L in image M. And this is done using alpha from my left pixel and other probability functions that we know to express in this phase, since I know the depth. We will see example in the next slide. But since each pixel, each alpha can be expressed according to alpha from my left, then I can go from left to right and get all my alphas iteratively. And in the backward step, it's the opposite. Each beta is computed using known probabilities, but it uses beta from pixels to my right. So then I can go from right to left. This is the backward step, and calculate all my betas. And once I have all my betas and all my alpha, I can get the probability that I want to estimate. So there are proofs for these steps, and I don't going to prove them. But again, you can read about it more in the book. But it's just I want to show the algorithm for using the HMM for solving this problem. So let's go to the forward step. So this algorithm is being calculated differently for each source image. So let's just look at source image 1 in this case. So the leftmost pixel in the forward step is just calculated by the probability, general probability that the leftmost pixel is observed or not observed. So they just assume that they don't know if it is observed or not, so they use 0.5 in this probability. And then these 2 metrics, given that I know the depth and I know its visibility, then I can just calculate these probabilities using the this emission probability. So I just get numbers in this case, since I know theta and I know Z. Next, if I go to pixel number 2, then if I look at this formula, then I can use the transition probability to get these expressions. And these expressions are calculated from before. They are from the pixel to my left. So I can get their values. And again, I can calculate the emission probability based on theta and the visibility of this pixel in the reference in the source image. So this continues until I get to the rightmost pixel. So I get all the alphas that I need. And now I go to beta computation. So in this case, I start with the rightmost pixel, and it can be shown that the beta for my rightmost pixel is just 1. And then I go from right to left, and each time I can calculate beta using known probabilities and the beta to my right, which are already calculated. So this is called the backward step for calculating all betas. And once I know all betas and all alpha, which are all just numbers, I can infer all the Z, all the probability for pixels being observed or not, which was my goal. So the total algorithm is to initialize the depth randomly and then apply the EM algorithm. In the E step, I assume that the depth is known in the first iteration according to my initialization, and I use the forward-backward algorithm to find the probability that each pixel is observed. And then I go to the M step and I assume that I know the probabilities, and based on the probability, I estimate the depth. So this is being done iteratively. Once I assume that I know the depth and I found the probability of observe, not observe, and in the second step, I assume that I know the probability of Z, and I use it to find theta. And one more thing is that until now we talked about row in an order from left to right, but we could just define it in the same way for a column that goes from top to bottom or from bottom to top. Or we could also define it in the same way where we define the order from right to left. So what they do is they perform this algorithm each time for different direction. So that's their total algorithm. And let's see some results from their video. So this is a reference image. You see here is the random initialization, just look like a noise, and the first pass to the right define initial depth. You will just see the depth, not the probability functions, but the probabilities for Z are also defined at the same time for each pass. Okay, let's make it faster a little bit. Okay, let's see the probability maps for Z. So red means observed, blue means unobserved. And this is the final depth estimation. And you can see the corresponding 3D points from the reference image when we set their depth, the pixel depth, according to the depth map that we calculated with this method. Okay, let's see another example. Here there are 200 images, and they calculated their poses by a method called Visual SFM. And it's just a structure for motion pipeline. And here, this is a reference image, and its depths are calculated in the same way from, in this case, from left to right, and from up to bottom, and from right to left, and so on. And here they had to clean the sky, so they used some segmentation method. And you can see the final depth map, which we used to find this cool point cloud. Let's continue. They have another example with the Buddha, and for the Notre Dame, which we already showed for structure for motion, they use this algorithm to generate a dense depth map from the reference image. Okay, any questions about Zhang et al.'s method?
Yeah, regarding the maximization step. So at the E step, you just like assume that you know the depth. Then we would like to check the probability that this estimation was correct, right? So
no, not the estimation of the depth. I want to calculate the probability that the pixel is observed or not in each source image. Not the probability of my depth. I assume that I know the depth, and I want to estimate if the
right.
The probability that this pixel is indeed observed in the image.
Yeah. What I mean is that you guess something, you guess the depth, and then you would like to check that your guessing was correct.
Yes.
But how do you check it?
Once the computer got stuck. So I just assume that my depth was correct. And then if I have depth, the depths are theta here. Given that I have depth, I can calculate the probability for the observance of each pixel. I can calculate the probability of Z if I know the depth, but I don't know the depth.
If you
So
know it, so how
if I
can
know
you
it, I can calculate the probabilities
how?
with the forward-backward algorithm that I described. It's just a linear algorithm that solves it very efficiently. It's just a solved problem. You can see this slide again, but it's just a very simple algorithm that if I know the depth, I can calculate the probability of the each pixel observed or not in each source image. I can calculate it according to my model, which might use too many assumptions, but I can calculate it.
It's using the normalized cross correlation.
Yes, that's the main metric for the likelihood of my observations. But I also have this probability transmission between states of observed, not observed between neighbors. So I have some smoothness between neighbors that I also use. That's the idea of these graphical models. They have different states for L pixels, which are denoted by Z, and I have probability for each state. And I have, this is called the probability of latent variables. Then I have the transmission probability from nearby states, which is computed according to one direction. It's called a chain, actually. And I have the emission probability for my observations. So I do not observe Z. I only observe the patches. So I have a probability for observing the patch given that I know its state. Without knowing its state, I don't know anything about its probability. I don't know how to use cross correlation if I don't know if the patch is visible or not. It will just tell me nothing correct. So I need to know the latent state in order to calculate the probability according to the normalized cross correlation. That's
of course. And you said that there are three choices at the start. You can just use the previous parameter or take one randomly or another one. So
yes.
What's the intuition behind that? Like, you said that like to give us like a more probability to choose the neighbors, but like what's the intuition behind taking a random guess?
Okay, so basically it's a very surprising result, I think, that was introduced about, I think, 12 years ago. I think, Meravi, if you know, I think in 2009, patch match was calculated.
Can you see the slide?
Yeah.
Again?
So the idea is that this works, and the reason that it works is that sometime you might get a random guess correctly, and then since you have a relation between neighbors, you once you get a random guess correctly, then all of your neighbors very fast are going to converge to your successful guess. Because once you get a good guess, then probably your neighbors will use it as well, because their probability to get a random guess is lower than just you. Then once you get your good guess, then you will just prefer to use what you get. So it's just a waving hands, but you can read the patch match paper. It's not their idea. They just apply it.
Okay, but the random
what
means the random here in the set. Also, what is the theta L? But random here is just one random guess, or it means that
one random guess in the range of depth that you assume. You assume some range. You don't want to predict something in 100 kilometers. So in this case, you assume that the fountain is between 5 meters to 12 meters according to the sparse triangulation, and you assume this range and sample from this range, not just sample from any number. Theta L is from the previous iteration. So in the first iteration, you don't have this. Okay, yes?
Can you explain again in this formula, we calculate 3 times, right? For L-1, L, and random. And then we choose the minimal one, right?
Yes.
Okay, and one more question. Rho L M. It's a cross correlation, normalized cross correlation, right?
What normalized cross correlation?
Rho,
Oh, yes, it's a yes.
so cross correlation, it's a vector because we have not only one pixel, we have the entire image to compare it.
No, here you have the cross correlation between 2 patches, so it's in one number.
Okay, so what I'm asking is, I need to compare not only one patch to another patch. I need to compare one patch to all the patches that in the image.
No, but for here for each suggested depth, you have one patch, right?
Okay, after I let's say
you test 3 depths. So for each tested depth, you have one patch, and you can calculate one number for cross correlation.
Okay, so I'm using the formula from the homework with this depth, and then I got my cross correlation for specific depth, for specific patch.
Exactly.
Okay, thank you.
But I haven't read what I've said, but what I'm not totally understand is that when you randomize the guess, so you have a chance to refine it, or like what if we just we worked on the fountain itself, then we moved to a pixel on the back wall, and we just randomize something. It's slightly better than our initial guess from the neighbors, but it's not good. So do we have a chance to change it during
always in each iteration you use random sample. You never stop to randomize. But probably if you had a good guess, then you will not choose your random again. You will always choose your previous guess or your neighbor previous guess. You will keep randomized selections, but you will probably not choose them. Okay, I think that it's a very for this paper it's technical point. If you want to read more about patch match, you can refer to the paper that Merav sent. It's not the main focus of their method. It's just some way to accelerate it, okay, and to apply some smoothness. Okay, let's continue. I'm wondering if we want to take the break now. What do you think? Do you want to take a break now or after Colmap?
I would say let's take 5 minutes break and not 10 because you have a lot of material to cover.
Okay.
Is it fine with you, Yoni?
Yes. Let's meet then in 5
past 10.
Okay. So I'll pause.
או שאתה מגריל אחד.
Guys, sorry, we need to continue. Keep the discussion after this lecture. Okay, so let's continue. I know that some notations were a bit confusing, and it's not an easy paper. It took me a while to understand, also to think how to present it. But I think that if you go over the slides again and on the talk, it will be more clear. Anyway, the reason that I added this paper is because Colmap, which is the state-of-the-art method for multi-view stereo, actually is an extension for this paper. So basically, if you're not using deep learning, you want just to get off-the-shelf solution, you will take Colmap for multi-view stereo. So that's why I wanted to review Zengetal's method. And now that we more or less know what they did, Colmap just shows some improvements to this paper, which are listed here. So we will go over some of them. So the first improvement is that they estimate the normal of each pixel, not just its depth. And the reason for that is that this mapping using homography of the assumption that the plane is front or parallel to my reference image is not correct when the surface has a different orientation than front or parallel. And then this mapping using homography distorts the patch, which results in lower normalized cross correlation. So basically what they want to estimate the normal and the depth, and then define the mapping according to the oriented plane. So that's the first improvement. And then in the M step, when previously Zeng et al. Needed to estimate theta, Schoenberger et al., which I will call Colmap, need to extract also the normal based on the cross correlation. So that's how it looks like. And for the patch match, before they had to choose between 3 options, but here they have 7 options. Keep the depth and the current normal, keep the normal and use random depth, keep the depth and use random normal, use random for both of them, perturb the current depth and slightly and use the current normal, use current depth and perturb the normal, and use the normal of my neighbor pixel with propagated depth. So now I'll talk about this, which I think is the only thing that is not trivial. So if for my left pixel, I have the normal, then I can define the local surface of this 3D point, and then I assume that pixel L is on this surface. So I set its normal to be the same normal, and also I know its depth by intersecting my ray through this point with my local surface. So this is the propagated depth according to the normal. So it's just one of the options that they test. So they test 7 options instead of 3. So that's the first change. Another change is to use geometric prior for view selection. So in Zeng et al., they use the probability that pixel is observed in image M or not observed in image M to define the probability to sample this image. But in Colmap, they define another 3 metrics for deciding whether we want to sample a camera image M, source image M or not. So we'll go over this alpha, beta, and kappa. So that's another different. So the alpha prior is the triangulation prior. Maybe we discussed it a little bit in the course, but when the angle between the cameras, when we triangulate a point gets very narrow, then the depth of the pixels that we want to triangulate gets very noisy according to the noise of the pixels. So what they wanted is to prevent using camera M if it's defined too small triangulation angle. So they have a way to measure this angle, but what they define here is that if this angle is below 1 degree, then I want to reduce the probability for sampling for using a camera M. Okay, so that's what this formula show, and it defines. So if alpha, if this angle is larger than 1, then the probability will stay 1. Okay, for example, because in this case, the minimum of 1 and my alpha, which is larger than 1, will be just alpha bar, and I get 0 here. So the probability will be 1. But if it's lower than 1 degree, then I will reduce my probability dramatically, such that if the angle is 0, the probability will be 0. So that's a triangulation prior. Another prior is the resolution prior. So basically, when we compare patches, we want their resolution to be similar. So we define the area of the patch of the reference camera and the source camera M, such that we want to avoid cases that there is a large difference between, or large ratio difference between the patches. So, for example, in this case, BLM divided by BL is very small, so I want to give small probability for sampling camera M. Another prior is the incident prior. So basically what we want to avoid is that camera M will be behind the surface. So we define this kappa angle, which is the angle between the normal and the vector from the point to the camera. So if this angle is too large, I don't want to use this camera. So we want it to be between 0 to pi divided by 2. So basically, we want to give less probability to large angles. So that's what it means here. So if the angle is low, it means that the camera is in front of my surface and I want to use this view because this angle is low. So that's more priors that they use, just heuristics that help them. Another heuristic is to use view selection smoothness. So Zeng et al. Defined smoothness between neighboring pixels, as we discussed. But in Colmap, they defined also smoothness between time steps of the iterations. So basically, they don't want, they want to control how much a state is changed according to the time, the change of observed, not observed. So this is defined by this matrix. So, and lambda t is changed over time. So at iteration 0, lambda t is just 0.5. So I don't care if states are changed, nothing is clear at this point. But a later iteration, and especially at iteration capital T, the last iteration, then I get capital T divided by 2t, which is 0.5. When I sum them, I get 1. So I don't want a state to change over the time. I want them to be smooth in more advanced iterations.
But if they choose in some iteration the normal to be random normal, so might significantly change Z, right?
It might be, but since your decision of choosing random normal is based on normalized cross correlation, so you probably won't do that if it reduces your likelihood. So we just choose this random only if it is improve your likelihood. So, but this is related to the states of observe, not observe. You don't want jumps in your probability map. You don't want to have one iteration, everything 0, and then everything 1. You don't want to have these jumps into your probability map of observe, not observe. So over the time, they want to reduce its chance to flicker. Just what they did here. Okay. Okay, another prior is geometric consistency. So basically, until now, we talked about reference image with, and I want to predict its depth and normal. And using this, I can map this pixel to its corresponding pixel in camera M. But then I can now use camera M as my reference camera, and then calculate theta L prime and NL prime for this point. Then I can map it back to the reference image and then measure this reprojection error psi. So basically, if everything is correct, I expect to get a small reprojection error and large reprojection error if it's not correct. So they use two modes. One is without geometric constraint, consistency, and in this case, we will choose the depth and the normal using only the cross correlation metric. And with geometric consistency, they will add to this also this geometric consistency term, but they bound it by some psi max, such that it will not explode and affect too much the solution. But just some multi-view consistency metric, not just one view consistency. Okay, so that's another improvement. And the last thing is some weighted normalized cross correlation, which I'm not sure if I want to skip. Maybe I'll skip it and we'll discuss it if we have time. It's just some heuristic way to do normalized cross correlation better. Okay, so let's see their results. So as you can see, it's just an improvement to Zeng et al.'s method. That's why I had to talk about Zeng et al. Before. And Colmap, what you see here is the state-of-the-art results for multi-view stereo for today if you're not using deep learning. And the disadvantage of using deep learning is that you need to train your images on some domain, but in Colmap, you don't have to do this. So if you get just a new domain, you get lab images without ground truth depth, then you will not be able to train a multi-view stereo network. So probably what you are going to do is to run Colmap. And I think that this is surprising because they use probabilistic graphical model, which is a very, it's not a deep learning techniques, and it was used before, and most applications that use it replace their method to use deep learning, but still Colmap uses probabilistic graphical models. There is another filtering step which I omitted, but you can read about it in the paper. It's just multi-view consistency filtering for removing points from the depth map. So any question about these improvements? They're all clear. Okay, cool. So here you see image depth normals, image depth normals for several images in different places in the world. So let's see some videos. In this video, they compare their results to the practical state-of-the-art method at this time, which called PMVS, which we did not discuss. But here you can see some comparisons between the reconstructions. So okay. So you can see that Colmap is more dense and also has less holes compared to the previous method. Let's see more examples, like the example of the Vatican. Okay, just to, there are 7,000 images here that were used to generate this reconstruction. So again, look at this wall, it's much more dense with the Colmap.
When you say that those methods can be improved using deep learning, so which, like, how do you use it? Like, in which steps? So you replace the whole flow?
Yeah, so in Colmap, if you can use Colmap and improve it. I don't know why they did not do it until now, but instead of using normalized cross correlation, use patch similarity. I think that would be a trivial improvement, which maybe they did not do it because it needs GPU or something. But this was one improvement. What?
What is patch similarity?
We talked about Spontar and LeCun paper that in the last lecture that this network gets two patches and return same or not same. Okay, so I can just use it to calculate score of patch similarity instead of normalized cross correlation, which is a heuristic score. You can use a learned score. But I also think that they don't want to use learning because they want this pipeline to be learning free, not to be restricted to any domain, just be a general domain problem solution. And it is free, it's open source, you can download it and run it on your images that you're taking with your phone, it's probably going to work. So it's a recommended experience if you are interested. Okay, let's see some quantitative results. So they checked their method on the fountain and the Hertz images, scenes, which has a LiDAR ground truth, and they calculated the fraction of inliers. So, for example, 14, which is the method of Zeng et al., got 77% inliers that their error is less than 2 centimeters in terms of depth. So you can see that it's less accurate than their full method, which got higher
How
accuracy.
do you measure that? How they gather the ground truth?
They use LiDAR, very, very expensive LiDAR to get ground truth for this data set, like dense and professional LiDAR. At this time, there were only this, I think this was the only ground truth because it's so hard to get ground truth for dense depth estimation, but today there are more data sets like the ETH data set and more data sets, but not always the ground truth is so accurate. So it's very hard to get accurate ground truth for depth estimation. You can see that if they use their method without normals, the results are much worse than their final result, but still better than et al. And the other geometric priors and temporal smoothness and the weighted normalized cross correlation did not affect the results too much in this case, but they probably needed it for the large scale scene of 7,000 images. And without
28, which is 28?
20, what 28?
Citation 28.
I'm not sure. I need to look in the citation list. But it's one of the previous methods, non-deep learning one, like
Okay.
maybe PMVS or other
Okay.
methods. Yes, it's surprising that it got better results in Hertz. Okay, so this no geometric prior, no temporal smoothness, and no weighted normalized cross correlation did not affect the results, but the geometric consistency of multiview did affect the results. Okay, so we discussed non-deep learning approaches, and now let's talk about the plane sweep approach very briefly, and then we will have time to go to deep learning approaches. How much time do I have? I don't want to.
Half an hour.
Okay.
No, it's 10:31.
Okay, great. So we are good. Okay, so the plane sweep algorithm uses this the fact that we know how to map frontal-parallel planes from image 1 to image 2 using homography. So at each step, I assume that I know the depth of all the pixels in the image to be Zi. So here I assume that all pixels of image 1 have depth Zi. Then I know how to map all pixels from image 1 to image 2 because all of them are on the plane. That's my assumption. But since I have this homography, I can also map all pixels in image 2 to image 1. And then this mapped image defines some metric on my assumption. Because if my assumption is correct, then if I look at pixel x, y, and I compare it to the mapped pixel from image 2 to image 1 at pixel x, y, if my assumption y was correct, then I should get low distance after this mapping. But if it's not correct, I will get high distance. So it's actually defined the cost for pixel x, y for the assumption that its depth is Zi. We will see an example soon, but that's just the high-level description. So I get a cost volume for each pixel xy in my image for assuming that its depth is zi. Okay, using this homography mapping. But then I
the
can
distance is pixel wise.
Yes.
I mean you measure the distance between the pixel and the mapped one.
Yes, the distance in the
Okay.
pixel after the mapping.
Okay.
Yes, so it can be the minus normalized cross correlation or a sum of absolute differences, but general thing. So that's actually define the cost volume because I have for assuming zi, I can get a cost image for zi for z min, for example, and then I increase the depth and get different cost images, and as a result get a cost volume. Okay, let's see the example and then see if you have more questions. Okay, so but this can be applied on more than two cameras. So for example, here I have 3 cameras, and I assume the depth for all pictures in my reference image 1 to be at depth zi. Then I have homography that maps image 1 to each different source image, and then I can map back each time one source image to my reference image and define the cost image between the mapped image to my original image 1 for this assumption of depth, and get the cost image, and then get several cost volume. For each nearby image, I get a cost volume. So let's see an example, and then let me know if you have questions. So here's an example. Again, our fountain example that we show a lot. So here the reference image is image 1, and we have 2 source images, image 2 and image 3, and you can see their cameras. Okay, so first I assume that the entire depth of image 1 is almost 6 meters. Okay, so according to this assumption, I can have the homography that maps entire image 1 to image 2. So I use it to map image 2 to image 1, and this is the mapped image 2 to image 1. Now let's see image 1. So if we flicker between them, we see that our assumption, we have low difference in this area, but high difference in this area. So our assumption for this depth is more correct for this area compared to this area, the image. And therefore our cost image for assuming a depth of 6 meters will look like this. We get low cost for these pixels and high cost for these pixels. So that would be the cost image. But for generating cost volume, I consider more depth. Let's see the mapping from image 3 to image 1 when we consider 6 meters depth. And again, you can see that it is correct more or less in this area and not correct behind. So, and that's the cost image. And if we look at the ground truth surface, we see that our assumption was indeed correct only for these points. Okay. Now we choose larger distance and map image 1, image 3 and image 2 to image 1 according to this depth assumption. And then I get this pattern of cost images. Okay, so it means that my assumption for depth 7 meter point 75 is correct for these pixels and these pixels, and not correct for these pixels and the wall pixel. And indeed, if I plot the ground truth points, I see that this is exactly correct. You see that it's noisy, but still give us some information about our assumption. And the last depth is 8 meters, 0.7. So here after the mapping, I see low cost for the wall pixels. also for these pixels, but this is wrong. And here you can see image 1 twice, and image 3 mapped to image 1, image 2 mapped to image 1 according to this depth. So if we flicker between them, we see that now the assumption is not correct for this pixel, but it is correct for the wall pixels. And indeed, if I use the ground truth, I see that my assumption was correct for the wall pixels. For the wall points. Any questions about this plane sweep idea?
In your cost function, you calculate the distance. You said, what is the function of the distances?
Here I used minus cross correlation, but you can use other distance metrics. Probably the best thing to do is to learn the distance metric, which we will see in the next paper that I will show, but here I use the minus normalized cross correlation.
Also, in this example, you show only 3 depths, right?
Yes. Usually you take much more.
Yeah, this is what I wanted to ask. The depth are more continuously, so you need to like do very small steps between them.
Yes, it make you do discretization to the depth, which might be problematic. By the way, in Zeng et al. And Colmap, they did not do any discretization because they randomly sampled continuous depth each time. So they did not have to do any discretization for the depth. And indeed, the problem with cost volumes is that you need to do discretization to the depth that you are looking for.
Also,
that's a disadvantage.
I don't think you can sample something that is not discretized. How can you perform an infinite set?
I mean, here you cannot use infinite cost volume of infinity size, but in Zeng et al, they just randomly let your depth to be chosen. So you could choose any depth.
Right, but implicitly it is discretized. Just
okay, yes, until the precision of your machine, but
right.
Yes, of course. But if we talk
more question, I see this in the last depth. You have a huge area in the center that are with low cost. Yes. How do you know to filter these errors?
Yeah, so I don't know, and if we get closer, you see why. The mapping is very smooth according to this direction. See just parallel lines, so it's probably why we get low cost here. Because it moved them, but you don't know that because it moved them to the right. And then it did not change their appearance, although this assumption was not correct. Yes, it's a problem. So basically, if you want to use a plane sweep, you need to take these cost volumes and not just take the winner takes it all solution, but to do some smoothness or aggregation, use semantic information, not just use this cost volume as they are, because you will get a noisy solution. So a method that used plane sweep needed to use smoothness constraints and other ways to aggregate information between different cost volumes. First, for each cost volume itself, we saw in the last lecture that for a specific cost volume, you need to apply smoothness constraints, otherwise there are unconstrained pixels. But here you don't have one cost volume, you have two cost volumes when you have two source images. So you need also to think how to aggregate between different cost volumes. So it's another level of difficulty that you need to consider. So, so there are classical ways to do that. I just wanted to show a deep learning way to do that. So there are three questions, right? One is how to compute a similarity metric between patches. So that's something that deep learning knows how to do. Second question is how to aggregate information in one cost volume. And the third question is how to aggregate information between different cost volumes, because for each nearby frame, I get one cost volume to the reference image. Okay. So let's talk about this paper, Deep MVS. So this paper published 3 years ago. It was published concurrently with another paper called MVSNet. You see that the name are not so different, just deep or net or things like this. So it was published 3 years ago, and it was the first end-to-end method for MVS. So in high level, we'll go into the details. They have a reference image, and they use nearby images to define plane sweep volumes, which they use together to calculate a disparity map of the reference image. And here you can see some sample results. So that's the high level. Now let's go into their architecture. So basically what they do is to take each source image and then generate its warped version to the reference image according to the assumed depth, as we discussed before. So V0 to VD-1 is just, each one of them is a warped version of V0, in this case, according to the depth assumption. So that's the first step. It's identical to what we saw before. But then instead of calculating cross correlation, as we did in the example of the fountain, they used convolutional layer to extract features from each image to get 64 features for each pixel. So the resolution of the image is 64 by 64. So originally 64 by 3 RGB. And then they extract features from each pixel, which are learned features. Then they concatenate the features of the images that I want to match to calculate cost image between the two images. And then the concatenated features are aggregated in order to express the cost of the assumption that these two images are matched for each pixel. So for each pixel, instead of having one cost, as we had in the normalized cross correlation, which we marked with yellow and blue colors, here they have 4 feature number representing the cost in some way that the network used. Okay, so we started from warped images according to different depth assumptions, and then I get cost information for each pixel according to this assumption. So it's actually define a cost volume for each source image. So this is the cost volume. It's 4 by D by 64 by 64. 64 by 64 is the resolution of the image, and since they have 4 numbers for each cost, they have 4 by D dimension in the depth dimension. And then, as we said, even though I have a feature, I have cost information, the question is now how to aggregate the cost into consider smoothness, and here they also consider semantic information. So they took the reference image, put it into VGG network, train on ImageNet for classification task, and use these features to aggregate information also for the cost volume. So let's just say that they have architecture called UNet to aggregate information in this cost volume. So in this case, they had 100 depths. So the dimension is 400 because they have 100 times 4 for the cost. And in the end, they got 800. They had 8 dimensions for each cost. So it's the aggregated cost, and they use semantic information during this aggregation. So they concatenated convolutional features from the VGG inside this operation. So this aggregation can learn both smoothness and some semantic information. For example, if I see car and a wall behind the car, if I can understand that it's a car, maybe it can give me information about the depth of the car relative to the wall. So that's what they call intra-volume feature aggregation, because all what we described until now was done only on one source image separately. So, but as you remember, in multi-view stereo, I have several source images, which I want to use all of them. So basically what I did until now is to get aggregated cost volume from each source image to my reference image. So if I do this for all my source images, I get, and I have n capital N minus 1 source images, then I get capital N minus 1 cost volumes, aggregated cost volumes. Okay, so that's the first part. Then, as you remember, the question is how to aggregate all these cost volumes together to get one consistent depth estimation for my reference image. So what they did in order to be invariant with the order of the images, because they say they don't mean they have no meaning, the order of the image, they used max pooling to get one aggregated cost volume, which they used more convolutional layers to improve it and eventually get an image of size, a volume of size 64 by 64 by capital D, where capital D is the number of disparities that we consider. So actually for each disparity that we proposed, they have the probability for each pixel having this disparity. So it's actually a classification problem. They discretize the disparity and they know the ground truth disparity for each pixel, and if the loss is the cross entropy between the vector of probabilities to the vector, one hot vector of the ground truth probability. So that's the training, and for having ground truth, they needed a lot of training data. So as we discussed, it's very hard to generate ground truth depth in real world situations. So they generated synthetic data set. And they also had some real data set that they used. Like here you see this real images with corresponding ground truth depth. And here you can see some of their results, qualitative results. So the reference image and the depth of the reference image. And here they took the reference image and used it with the depth for novel view synthesis. After you have 3D, you can just move the camera and see novel views by the depth and using the new camera, the new view. Here's another example. So these are just qualitative results. Let's see some comparisons, qualitative comparisons. So on the left, you can see the reference input image, the ground truth depth, the results by Demon, which is a method that can only use 2 images. So I'm not sure why they compare to it. And the results by Colmap, which we discussed, which has 2 versions, filtered and unfiltered, and their results. And qualitatively, you can see that they got the best results without filtering. If you filter with Colmap, they get more accurate results, but they throw away all the outliers, so it's less impressive. Any questions till now?
Again, the most important to understand in this case that we need to have the ground truth.
For training this
Yes.
network, yes.
For training this network. So if we don't have ground truth or our domain, we cannot use it.
Yes, but it's one paper. There are more papers. Some of them considered unsupervised learning problem. But this specific paper used the supervised approach. So they need ground truth.
And this is the best state of the art.
No, it's the first multi-view stereo, end-to-end multi-view stereo that use deep learning for disparity estimation in multi-view setting.
And if we're looking on the state of the art of the deep learning, what is the best geometrical error that we can achieve?
For this specific benchmark, I'm not sure, but there are a lot of new papers. One of them are under review and not published yet, so it's hard to say. But you can look at the benchmark, for example, on this dataset called the ETH dataset on Tank and Temples, and I think they have a ranking of the different methods, so you can see what method gets the best results in these benchmarks.
Thank you.
So still you can see that Colmap without training is not so bad, even without filtering at all. So it means that there is still gap to achieve here. And I think mostly the discretization and resolution problems and training issues. Okay, let's see what happens if we don't use synthetic data set and just use on a very small data set of with ground truth, then we get some artifacts in the output. Here's another interesting comparison. Here they limit the neighboring number of views and show the results, for example, when there is one neighbor. So you can still compute the disparity from two images, but it's very noisy. But with more images, it gets better. What's interesting is that they are less sensitive to the number of views. So, for example, if with one neighboring, you see a large gap between their method to Colmap, and I think that it is probably because they use semantic information. So they don't need the multi-view consistency of Colmap to get good results. But after 5 images, more or less, it's not so matter for these two examples. You can see that the performance of the two methods are very close. Okay, any questions about a deep MVS paper?
Can we train this network with ground truth made by Colmap?
Yes, sometimes people do that. But then they use the filtered images, which, for example, has only 70% of the information of the pixel, and hopefully the trained method will know how to complete the missing pixels. But since it's never got supervision for the 29%, then it might not work well in this area that usually Colmap filter. So usually the supervised method really needs ground truth, and it's possible if you don't have enough data, it's possible to train on synthetic data together with real data, and then the domain gap is being closed.
I have 2 more questions.
Okay.
If I trained my network on, let's say, 8 images, when I do inference time, I need also 8 images.
No, so they actually used 1, 2, 3, 4 neighboring in training phase, and in inference phase they used more images, and you see that it learned how to use more images. So maybe in this case it did not help them. You can see that the orange curve got a little bit up compared to the Colmap that always gets better results with more images. But overall, they were able to generalize to more neighboring views. Okay, so just to sum up, and today we talked about the multi-view stereo problem, where we are given camera poses and images, and the task is to extract depth map for each input image when we consider it as a reference image. Now that we have these depth maps, it is possible to fuse them to one dense point cloud, and then to use this fused point cloud for estimating the surface of the from these 3D points. So these two parts of depth fusion and surface reconstruction are omitted from this lecture because we had a lot of methods to discuss, but I'll just say the surface reconstruction has a Poisson surface reconstruction algorithm, which has a very known and closed way for computing. And depth fusion is also done in Colmap, so you can read about this part in the Colmap paper. So that's it. Thank you. And if you have more questions, let me know.